Okay, good morning, afternoon, or evening, everybody. I'd like to welcome you to the Are You Ready to Python? An Introduction to Working with Land Remote Sensing Data with R and Python Earthdata webinar. This is your host, Jennifer Brennan. While everybody is logging in, we have two optional polls at the bottom left and middle portion of your page, and we certainly appreciate your feedback on these polls. I've got 2 p.m. Eastern Daylight Savings Time, so we are going to go ahead and get started here. What I'd like to do first is go over a few logistics related to this webinar. To ensure best audio experience, the conference has been placed in silent mode. However, if you have any issues or you have any questions, what I'd like for you to do is enter those into the Q&A pod, and that's located on the lower right-hand corner of your screen. This works like a chat. As far as the webinar being recorded, it is being recorded. The recording will be posted to our online Adobe Connect webinar catalog as well as to our NASA Earthdata YouTube channel within a few days of completion. And I will make all presentation files available for you to download at the end of the webinar. Regarding timing, this webinar is 1 hour long. We've allocated 45 minutes to the presentation and live demonstrations with an additional 15 minutes for the question and answer period. After our speakers have finished their presentations, what we'll do then is we'll move to a final set of polling questions, and then from there we'll transition directly to the Q&A period. You will have an opportunity to ask your questions throughout all portions of the webinar, with the exception of the live demonstration by using the Q&A pod. Again, this works like a chat. Questions will not be answered using the raising hand function. It has been disabled. And then just one final note, depending upon the volume of questions that are received today, we'll extend the Q&A period an additional 15 minutes to 3:15 p.m. Eastern Time for those of you who are able to stay on the line. What I'd like to do next is let's pull up today's agenda. I pull that up here. Okay. During the first half of the webinar, our speakers will provide an introduction to the Land Processes DAC. They'll show you how to navigate the NASA LPDAC website and also locate e-learning resources. Excuse me. We'll then transition to 2 short video tutorials that will show you how to download and execute both an ASTER Level 1T script and a VIIRS script. And then the second half of today's webinar will be spent on live demonstrations using both R and Python on Jupyter Notebook. Today we do have 2 speakers. The first speaker is Cole Crable, who is a remote sensing scientist at the NASA LPDAC. And then our second speaker today is Aaron Fries, who is a data scientist at LPDAC. With that, it is my pleasure to introduce our first speaker, Cole Crable. Cole?
Thank you, Jennifer. Good afternoon, everyone. Today, Aaron and I will be providing information and live demonstrations using R and Python to work with land remote sensing datasets archived at NASA's Land Processes Distributed Active Archive Center, or LPDAC. NASA's LPDAC is located in Sioux Falls, South Dakota at the USGS Earth Resources Observation Science Center, or AROS. It is one of 12 NASA DACs and is part of NASA's Earth Science Data Systems program. Being the land processes-oriented DAC, the LPDAC stores datasets including variables such as surface reflectance, land cover, and vegetation indices of the land surface. What is the LPDAC and what do we do? The LPDAC is made up of over 40 staff working as part of an interdisciplinary team from scientists like us to software engineers to science communication specialists. We archive Earth science remote sensing data, distribute and provide open access to the data, offer user support, and conduct outreach to the user community. This webinar is a good example of those last 3 functions. Our user community includes over 170,000 users representing 126 countries. The products that we archive include mission products such as ASTER, MODIS, and the newly released NASA VIIRS products, as well as derivative products from NASA missions developed by PIs in the Earth science community. As Jennifer mentioned, we will begin by showing you videos highlighting e-learning and tutorial sections of the LPDAC website and how to find and execute our readily available Python and R scripts. Later, we will go into live demos of general uses for working with remote sensing data in R and Python. At the end of this webinar, we hope that you will know where to find our available tutorials and how to execute them, and have a better understanding of how to work with land remote sensing data in R and Python. R and Python are both great candidates for working with remote sensing data for multiple reasons. First, they are efficient. They are quick, easier to use than higher-level programming languages, offer appealing user development environments such as RStudio or Jupyter Notebooks, and are reproducible. On a similar note, they also allow users to batch process and automate some of the steps needed to pre-process and process satellite data. This is a huge benefit if you are working with mini files where the typical point-and-click manner of performing these steps in GIS or remote sensing software may be extremely time-consuming. R and Python are also efficient because you can do everything from downloading, pre-processing, processing, and analyzing the data all in the same place. And of course, we would be remiss in not mentioning that both are freely available. But moreover, both are widely used within the remote sensing and GIS community, but also in many other disciplines as well, which means that when you do encounter issues, there is good documentation and a large user base to help you overcome those problems. In order to download data from the LPDAC data pool, you will first need to provide your NASA Earthdata login account credentials. The LPDAC data pool is where we store all LPDAC land remote sensing data, which we can see here. If we click on VIIRS, we see a list of directories showing the 4 VIIRS surface reflectance products that were recently made available. If you go into a directory and actually try and download a file, you will be prompted for your NASA Earthdata login username and password. If you do not have a NASA Earthdata login account, you will need to go to the link provided and set up a NASA Earthdata account and authorize the LPDAC data pool. It is free and very quick and easy to get signed up. Here is an overview of the data products that we will use in today's presentation. We will begin by showing how to convert ASTER Level 1 Precision Terrain Corrected Registered at Sensor Radiance, or ASTER L&T, from digital numbers to top of atmosphere reflectance. We will specifically be looking at the ASTER Visible Near Infrared, or VNIR bands, available at 15-meter resolution. Next, we will look at the Visible Infrared Imaging Radiometer Suite, or VIIRS, and how to deal with HDF5 EOS files. As aforementioned, VIIRS surface reflectance recently became made available on the LPDAC data pool, and we will focus on the VNP09A1 product today. But there are actually scripts available to process all 4 of the new datasets. VNP09A1 is an 8-day global 1-kilometer product. We will wrap up our presentation by showing how to leverage a peer's quality services to access quality info from one of our MODIS vegetation indices products, Mod 13A2 version 6. Now I will hand it off to Aaron, who will show where to find LPDAC e-learning materials and how to download them.
Okay, so we'll give a quick video demonstration of the website. This is the LPDAC website, lpdac.usgs.gov. This is where you would come to find data sets that we have, find any tools that we have, any resources that we might offer regarding the usage of our data sets. So if we go into this user resource dropdown, click this e-learning. You're taken to our e-learning section where we have webinar material, tutorials, video tips, things to help you use our data. You can click on these individual tabs to filter the material. You can filter the material also by using this search dialog. So if I start putting in VIIRS, I get one tutorial in return, and I can click this link, and it takes me to a landing page. So all of our scripts and tutorials that we develop have a landing page. They follow a pretty strict structure. We have an objective section that gives you kind of the idea of the purpose behind the script or tutorial. We have a prerequisites section that gives you an idea of the systems that we've tested it on, the programming versions that we've tested, the dependencies that you would need to download in order to use it. And then a procedure section that gives you kind of a quick start on executing one of our scripts. We normally have an R script or a Python script, and this gives you kind of the first steps to execute those scripts. And then we have a related tutorial section that Any materials that are related to this specific tutorial or script, you can get links to those as well. So we're going to click into this Python script here. It will take us to our public-facing Git repository. So in this case, we're in a directory that contains both the Python and R script. Most of our repositories aren't quite structured like this, but for this particular one, they're both in the same directory. If you're familiar with Git, you can pull the data or the documents over to your machine in a couple ways. You can use the cloning function, so you can clone the repository to your machine. You can use the download function that will download a .zip file onto your machine for the entire repository. But in many cases, you're interested in a single file. So in this case, we're going to click into the Python script to get the text representation. And then we will go up into this right-hand corner and click Raw File, and then do a right-click, Save As. And then what we want to do here is remove that .text extension and change it to a .py extension. Then we'll click Save. And now we'll go and see where that's downloaded to. And there you go. You have your Python script from our Git repository. And so that's how you kind of interact with our landing pages and for tutorials and how to download scripts from our repository. And now I'll pass it back to Cole to give you a demonstration of this process.
So as Aaron mentioned, we can find LPDAC tools and tutorials on our e-learning page. You can sort by type of presentation, or you can search by keyword. These tutorials come fully automated, meaning that you simply need to download them, point to the files that you would like to be processed, and it will batch process the files for you. So here I'm going to type in ASTER L1T into the search bar, and we see here that we have a couple of tutorials on how to convert ASTER L1T from HDF to GeoTIFF. So I'll click on that first tutorial there. So this is our How to Convert ASTER L1T radiance to Top of Atmosphere Reflectance tutorial. This data recipe demonstrates how R and Python scripts can be used to convert ASTER L1T data from digital numbers to radiance, and from radiance into top of atmosphere reflectance. The scripts will do this for each of the visible near-infrared and shortwave infrared bands in a given HDF file. Note that if you are interested in using ASTER thermal bands, you should check out our How to Reformat and GeoReference ASTER L1T to HDF files tutorial. ASTER L1T data are stored as unscaled digital numbers. However, if users are interested in measuring the biophysical properties of a surface by calculating metrics such as vegetation indices, they will need to first convert the data to reflectance. The script will output GeoTIFFs for each ASTER band in the original digital number format as radiance and as top of atmosphere reflectance. We have created both R and Python versions of this tutorial, and here are our testing environments. All testing was done on Windows operating system. All testing was done using R version 3.3, and for Python we have tested both in Python 2.7 as well as Python 3.4. There's also a list of libraries you'll need in order to run the scripts. So moving down, here we see the procedures for both the R and Python scripts. First, we will copy the script. I've already downloaded an ASTER L1T file, and I've also already started an R session where we can open the newly downloaded script. I will show you how to change the input directory and execute the entire script in a second. So here I will click on the R script, and I'm brought to our Git repository that Aaron just showed everyone. I will download this script by clicking on the raw file in the upper right-hand corner of this page. And then once I'm taken to the raw file, I will right-click and select Save As. I will change this to all files. And the important thing here is to change the file extension to reflect that this is an R script, which is .r. And then we can go ahead and save that. Now I'll move over to my RStudio console. Here we can go to click Open. We can navigate to where we downloaded our new R script. So here we have our file. We will look deeper into what this script actually does in the next ASTER L1T live demo, where we will work interactively with ASTER L1T data in R. The big thing here is to change this input directory to wherever you have your ASTER L1T file stored, like so. Next thing I'm going to do is press Control-A, which will highlight the entire script. And then we can go to the upper right-hand corner again and select Run. So now R is running the entire script. Now I will move over to a directory where I previously ran the script. So here we can see an example of the ASTER L1T output files, including data for each band as digital numbers, radiance, and top of atmosphere reflectance. Lastly, I want to show you the actual results. So here we can see band 1, top of atmosphere reflectance, and we can see our data is spatially referenced with the correct UTM zone applied. So now I will pass it back to Aaron, who will show us another readily available script from the LPDAC that works with VIIRS data.
Yes, so we put together some scripts and drafted some tutorials on how to reformat and georeference VIIRS surface reflectance HDF EOS files. And so to get to this, we will start on our e-learning page and start typing in the VIIRS to filter our list of materials and get to our tutorial link. So we'll click there, and we will be taken to our landing page for these scripts. From here, we can see the additional information regarding the purpose and the usage of the scripts. So the objective here, VIIRS data is our newest data set, and it's stored as HDF EOS 5 files. And because of this, a lot of our programs that our users typically use just don't quite or haven't caught up to being able to visualize these data in a spatial manner. And so this script will convert each science data set within the VIIRS file into a GeoTIFF so that it's easily brought into a GIS and remote sensing program. So these files will be georeferenced and ready to do any analysis that you want to throw at it. And so currently we have 4 separate surface reflectance products, and this script will actually work on all 4. So moving down to the prerequisites section, we've developed all of these, or this script on a Windows machine and haven't really tested it on a Linux as of yet. For R, we've tested it in version 3.3, while in Python we've tested 2.7 and 3.4. And so you can see the dependencies below. For the procedures, we always ask you to download the data first. For the R script, again, you're going to have to go into the script and change that in directory variable to the directory folder that you want the data, or that you saved the data. For the Python script, we've actually wrapped it up so that you can actually execute it from the command line without having to go into the script and changing anything. And so we're going to click into that Python script and go to the public repository. And then I'm going to click on the script on this screen, which will take me to the text version. And I'll click the raw file, right-click, and save as. And now I will change the extension from .txt to Python. And then we'll go to that folder. And so you'll notice that we have saved that VIIRS file in this directory. I've also went out and downloaded a file previously for HDF EOS, or this VIIRS file, specifically the 09A1 product. And so now we are going to very simply execute this script from the command line and create some GeoTIFFs for each science data set within the VIIRS file. So I'm going to go down and open up my command prompt. I'm going to very simply just type in Python. And then I will drag or add the Python script and its path to my command window. And then I'll drag and add my file directory. So something to note here, I copied over the file name. The scripts won't act on an individual file like this. So you have to take the path name down to the directory where the data is stored, and it will execute on all the files that are stored within that file. And so I'll hit enter. The script typically runs pretty fast. And so now we have an output location, and we will go there. we'll take a look at what we got for an output. And so these are all of the science data sets that are within the VIIRS file. And then we can take a look at these within or in ArcGIS. So we'll pull a GeoTIFF in. It's the M7 band, which is the near infrared band. And you can see that it comes up on the screen referenced correctly. And to kind of prove that, we'll take a look at the properties. You can see that the dimension information and the cell size information, as well as the projection information, has been applied, and it's georeferenced, so you can now perform your analysis on that. And so now you know how to execute the scripts from Python to get these georeference VIIRS GeoTIFFs. And so now I will hand it back over to Cole, who will start the live portion of the webinar showing how to process and interact with ASTER L1T files in R.
All right. As Aaron mentioned, now I will show you how to work with ASTER L1T data more interactively in R. To do so, I've created an R Markdown document, or R notebook. This is an ideal format for demonstrating how to work with data in R because it allows me to break the code into code blocks that I can then run and explain what each specific block is doing. So in this live demo, I will show you how to set up your working environment, define functions, read metadata, georeference raster arrays, and define coordinate reference systems. Also, we will look at how to subset specific datasets and apply our previously defined functions on rasters. Items 1 through 6 are all covered in our readily available ASTER L1T DN to Reflectance script that we showed earlier today. For today's demo, I will go a few steps further and show how you can take the output results from that script and visualize and plot ASTER data, including how to generate an RGB composite, how to calculate NDVI, how to visualize histograms and calculate statistics, and ultimately export your results to GeoTIFFs. So we'll start here by setting up our environment. So to execute a code block in our notebook, we click on this green arrow here. So I'll go ahead and run that. We'll start by loading the necessary packages into R, setting our current working directory, creating our output directory, and then creating a list of ASTER L1T files in our working directory. So for this demo, we just have one ASTER L1T file located in the directory. Next, we will set up our calculations. So there's two main calculations, the first from DN to radiance, and the second is from radiance to top of atmosphere reflectance. However, in order to perform these calculations, we will need to define certain variables beforehand, including the unit conversion coefficient, or UCC. The UCC is set by band and by gain designation. So in order to set up this list of values, we create what's called a data frame in R. So I'll run this block here. And so here below we can see the output where we set things up by band and by gain designation, which we will later use to call and select a specific value in order to calculate from DN to reflectance. Next, we can define functions for our calculations. So here we can run this, and we've set up our calculations, which we will later use to pass through the entire raster array in order to convert from digital numbers in order to get to top of atmosphere reflectance. Next, we will read the file metadata. So I'll run this here. The important call here comes from GDAL. This GDAL info call is going to report back all of the file metadata for the ASTER L1T HDF file. And there's a lot of it. We can see here over 400 lines in this very large string object. And it's all very good information, but we only need a few key bits of that information in order to do what we're looking to do today. So grep can help us with that. Grep, or regular expressions, is an extremely helpful pattern matching function. So in the code block below, we search for the very large object string in order to find the solar direction, or solar zenith angle, that's used in the conversion from radiance to reflectance. So I'll run this here. First, we just call grep and then a specific text string that we're interested in, and that returns us back where in that very large string object it's located. Next, we actually input that into the metadata object and it gives us the information provided on that line. We'll take it one step further and use substringing and as numeric in order to convert that to a numeral to arrive at 34.16, which is a value that we can then input into our function in order to perform our calculations. And so the reason why I spent some time explaining all that is because it's actually very important. Using grep and subsetting strings is a very important step in not only looking at ASTER L1T data in R, but in looking at all sorts of remote sensing data in both R and Python. So here is another example of how we use grep to search for the gain designation for each ASTER band. And so here we can print out the gain for band 1 for this particular observation is normal. Next, we can define our coordinate reference system. So I'll run this here. Basically, we are searching for our upper left and lower right bounding box coordinates in order to set up our extent. We will also search for the specific UTM zone that is used for this ASTER L1T file. And then we will use the extent call from the raster package in order to actually define that extent, which we can see output below. Next, we will compile our coordinate reference or CRS string to attach projection information to the rasters. So if we run this here and we input the UTM zone that we grabbed from the metadata, we see our proj4 string here with the correct UTM zone attached. Next, let's get a list of the science datasets using this get subdatasets call from the GDAL-utils package. So if we run this here, we are presented with all of the specific datasets within the ASTER L1T file, including the 3 that we will look at today, 2, 1, and 3N, the visible near-infrared bands. Next, we can set up each of the visible near-infrared bands. So I'll run this below, and then we also generate output file names, extract the band names for each file, and then attach the output directory. And so we can see in our output here, we have our output directory, our original file name, and then this is for band 1. Below is where we actually extract the specific datasets using GDAL, set the coordinate reference system, and define the extent. So here the big call is GDAL translate, which opens that ASTER L1T HDF file, extracts the specific subdataset we're interested in, and export it as a GeoTIFF. We can also attach the CRS by using this raster call here, and then define the extent using extent. And there we can see our extent for our raster layer. Next is where we actually convert DN to top of atmosphere reflectance. So I'm going to go ahead and run this, and we begin with some basic logic that defines the UCC value based on that high, normal, or low gain designation for each band. And then eventually we use the calc function in order to run the function over the entire raster array. And the reason why this block is so long is that we're doing it for all 3 of the bands. So again, I want to reiterate, everything above can be found in our ASTER L1T conversion scripts on the LPDAC website. What follows below is an example of how you could further apply your results from those tutorials. And so we're going to begin with a basic plot function, and this is coming from the raster package. So we can run this. And so here we can see we're just running plot and then our reflectance from band 1. And here we can see the entire ASTER L1T image. This is an agricultural field located in Saudi Arabia. However, next we want to actually crop this image. So we'll run this here. We'll set up a sub-extent here, and then actually use the crop function from the raster package to crop all of our arrays. And then a big thing here is to set your fill value equal to NA so that it's ignored in the plotting and statistics. And then we can go ahead and do a basic plot again. And so here we've zoomed in on those irrigated agricultural fields. Next, we're going to stack the 3 visible near-infrared bands. I'm going to start this before because it does take a little bit of time. But so here we're taking all 3 of the rasters and stacking them on top of each other using the stack call from the raster package. And then this plot RGB also comes from the raster package, which allows us to input the 3 bands composite, define which band goes to red, green, and blue, and then here we can see our output. And so here now we really see those bright green
agricultural fields from the surrounding desert environment. Next, we will define and compute NDVI using band 2 red and band 3 near-infrared reflectance, and then we can plot our results. So I'll run this here. We'll begin by defining our function for 2 bands, and then we'll actually pass each of the band 3 and band 2 raster arrays into the calculate NDVI function, and then plot the results. So here we can see in shades of green our higher NDVI from the agricultural fields compared to the surrounding desert environment. If we want to stretch the image, a good way to determine where those bounds lie is by plotting the histogram. So here we call the hist function on our raster array. You can define other things like the main title, so distribution of NDVI. And here we can see that there's a high distribution of desert pixels near 0, and then there's some irrigated agricultural areas here with higher NDVI. So we use that information to set this zlim parameter in the plot call here. We can run that. And so here we've set these specific bounds so that we can stretch the data a little bit better. We can also set things like the maximum number of pixels that will be plotted. And here we can see our NDVI image. So next, I just wanted to quickly show you guys how to calculate some basic statistics. Here we are going to use cell stats, which is coming from the raster package in R, to calculate statistics on our entire raster array. So if we run this here, we call cell stats, and then you can select whichever statistic you're interested in here. I've selected mean, min, max, and standard deviation, and then we can print out our results. And then last but definitely not least is to export our results to GeoTIFF. So I'll run this. We set up our output file names and then use the write raster function in order to export those to GeoTIFF. And then very quickly, I just wanted to show you guys the results. So here's the RGB image that we just created in R. And then here is the NDVI image that we just created in R with the different color map applied to it. And so that higher resolution in ASTER gives us a good indication of the health of the vegetation in this particular scene. All right, without further ado, I'm going to pass it back over to Aaron, who's going to show us how to work with VIIRS surface reflectance data in Python. Okay, so I'm going to show you this tutorial in Jupyter Notebooks. Jupyter is an interactive programming platform that allows you to display both code and rich text elements. It's great for tutorials. So I'm going to kick off a session right here. So while we're waiting, I'm going to tell you about the first tutorial. We created this VIIRS tutorial to kind of demonstrate how to process and interact with the VIIRS data. So it's an extension of the previous script that I just showed. And so in this tutorial, we'll bring in some VIIRS data, and we'll show you how to bring it into your Python environment and interact with it, and do some simple plotting as well. So let's click into it. So this tutorial will actually be able to be executed over all 4 products that we have, so the A1, G1, the H1, and the CMGs that we have. Toward the end, with the mapping functions, you would have to maybe tinker a little bit, but for the most part, to visualize and interact with the data, you don't really need to do much but change the input directory. And so we're going to start off by calling in the modules that we'll need to interact with these data sets. And so we're going to start with importing the H5Py library, which is essential for reading in HDF5 files, and then some just common geospatial libraries as well. So this cell block here, let's run all of these. Sorry for the jumping. So this cell block here, I am specifying the directory where all of my data is stored, and I'm creating a list object. And so I'm printing out that list object. I see that I only have one file in there. If I had multiple files, they would all show up here. In this code block, I am specifying a specific file. So in this case, I'm using the index 0, which means I want the first file in that list. And then I'll use this to add to the input directory name so that I can set up a path to a file where I can pull it in using that H5Py library. So this block will create a output directory for any GeoTIFFs that I create, any graphs that I create. They will be dumped in here. Something to note, the VIIRS data, the VIIRS tile data is on the same sinusoidal projection as our MODIS collection is. So what this will do is later on in the script we'll specify whether we're dealing with a tile product or a CMG product. And it will assign the proper projection depending on what it is exactly. And so let's dive into the data. Let's pull in that in-file location that we specified earlier. And so now we have the HDF5 object in my workspace. I'm going to strip the name off and remove the extension. And so this will be used in like outputs. If I want to output some GeoTIFFs, I would tack this onto the front with the layer name. Diving into the file a little bit, these VIIRS files have two main groups within, this HDF EOS group and this HDF EOS information group. Inside the HDF EOS group, there is more groups called additional and grid group. So this grid group is where all of the data or science data sets that are within the VIIRS file, that's where they're stored, along with some attributes that we'll need later on. This HDF Informations group has a struct metadata.0 element within it, and this really gives you the global metadata. So this will give you the origins and lat long. It will give you the dimensions. It will give you some other useful information. And this is a kind of a big metadata object that you saw in Cole's presentation. And we'll print that out in a little bit. But so this is all of the groups that are within the HDF file. This little code block shows you all the groups in their hierarchical order. And then you can see in this grid group, we have all the science data sets listed out here. So moving on, that metadata, struct metadata object. So we're digging into that, and we're creating a list of string objects, and we're going to use that object to get information that we need in order to georeference our output images. And so you can see we have things like upper left point in meters, lower right, projection information. All this can be used to make decisions or create outputs. So we'll take that object, and we'll do some string manipulation and pull out the upper left longitude and the upper left latitude coordinates so I can get my origin point. In this block, I am pulling out an element called grid name, and what this is used to set the projection. And so depending on this grid name, I can determine whether it's a CMG or a tile product. And so if it has CMG within the name, it will be assigned the geographic coordinate reference system, or if it's other, it will be assigned the sinusoidal projection system. So that's used in outputs. So this code block will list every science data set that's within this VIIRS file. You can see we will use this information either as an index or other to kind of do some further examples of some simple plotting here. And so we're going to call in the matplotlib library, which is a pretty common library in Python for plotting. We're specifically interested in the M5, the M4, and the M3 spectral bands, which correspond to the RGB, and we're going to plot these. And so I am referring here to that this data set object here, and I'm pulling out those RGB objects, And so this object actually contains both data and attributes in it. And so I can specify which I want to look at and what pieces I want to pull out to use later on. And specifically from the attributes, I want to pull out the scale factor here and the fill value. And so I'll apply those to the data and then plot those results. And so for these bands, they are the same, so the scale factor is the same between bands, and then the fill value is the same as well. So here I am from that R object pulling out the data values here, and then applying the scale factor for all three of those bands. And then in this last part, I am creating a NumPy data stack of the RGB bands, which I will then later plot. And then in this block, I am specifying the fill value for that data stack. And so when I do a plot, here is the true color image using the RGB bands. And so another thing you'd want to maybe do is, again, create the NDVI index. And so to do that, I need the near infrared band, I need the red band. And so again here, I am pulling out the near infrared band from that data set list, and I'm taking out the data from that object, and I'm applying the scale factor to that data set. And so that's the scaled NIR array. And then I'm going to apply the no data value to that array. And then I need to, in this case, apply the no data value to the red array as well. And so when I take this NDVI object, which is near infrared minus R, and divided by near infrared plus R, I get this image down here. Okay, so we can do a little bit more to make this a little bit more pretty. We can kind of restrict the values that are shown, and so we do a histogram to see where the values fall and kind of make a decision depending on what we see in this histogram. So we can then use that information to create our kind of final image. So in this image, we're adding a title. We're kind of given an idea of where the location of this tile is. We are restricting the data values that are to be shown, depending on what we see in this histogram, and we're applying that yellow to green color map again. And so that is our final output, and here I do a save fig, which it saves as a PNG, so I can have some distributable images, in this case not georeferenced. But this next block, which is hashed out, is the block that would actually run through each of those science data sets that we specified up there. It will use all the georeferencing information that we pulled from the metadata and apply that to the output and create a GeoTIFF. And so if you unhash this and executed it, it would cycle through all those bands and give you however many GeoTIFFs for each of the science data sets within. And so that's the VIIRS script. I'll jump right into the quality tutorial that we wanted to just show. And so this is based off of a web service that we developed a little over a year ago probably. And it's a service that is designed to go and decode quality values. So anybody who's familiar with MODIS quality knows that it can be a pain to actually decode the quality layers. And we tried to make it a little bit easier for our users by developing this service. And so this is a web service, and so because of that, we need to import this request module so that I can make service calls over the internet. And then I import the pandas library just to create some pretty tables at the end, just to separate the data and make it more legible. So let's kick this one off. Again with the jumping. Okay, so there's different pieces to the service. So depending on what you have built onto the service URL here, which is within our appears API that we have developed. If I add quality to the service URL, I will get all of the products with layers that have quality associated with them. And so this is only for Modis, our Modis collection at this time. And so a quick output view of this is after running that service, I can filter it down using some indexing, and this is what I get. I get a dictionary or a list of dictionaries that have all sorts of key value pairs that I can use to do some further filtering. So maybe I just want information about a particular product that I'm interested in. So in this case, I want some information on the MYD 13A2 version 5 product. I can do that in two ways. So I can use that list that I just created and perform some filtering on that, saying for this particular key, this product and version, I want this value associated with that. And for that output, I get two layers, the EVI layer and an NDVI layer, and both of them have this associated quality layer. Now, it's the same for both of these layers. You'll see that with most of our products. But that's really what I'm after. You can get the same results by using the service. I can tack on, along with the quality, I can tack on the product name with its version, and I can get the same exact results back from our service. And again, we're after this quality name, you can see right there, which I will then, again, add to the service and then make another request. And so the result of this request is basically all of the possible values that we can get that you would possibly run into in a quality layer. So this isn't very helpful, but if you take it a step further and add an actual integer value to the end of this service URL, you will get the actual decoded values for this individual pixel value or what have you. So to make that a little bit pretty, I threw that in the Pandas data frame. You'll notice, so for adjacent cloud detection, no. For modeling, it's good quality. Okay, and so if you're familiar with this, you would see that this is, or familiar with Modis quality, you would notice that this is out of order. The service actually returns the data values back in order, but Python rearranges them by alphabetical order. So to keep the proper order, we use this code block, and then we throw that data into another data frame. And now you can see this is in its proper order from for each of its bit words. Modeling, followed by VI usefulness, and then I can further drill into that data container and request a modeling bit, and then I can get that. So, but you're not limited to, in Python, to only decoding a single integer value. We've actually taken this and made it operational over entire arrays. We've done this for a Python tool that we developed for ArcGIS that will take in an array of data and create an output image that has been completely decoded. And so this is just a quick example of the Modis quality tool or service, which you can then kind of take and expand and use as you wish. So I think that's about all we have to demonstrate. I think I will hand it back over to Jennifer to open it up for questions and finish things up.
Okay, thank you, Aaron. Thanks, everybody. At this point, we'll move to the final set of polling questions, and we'll give these just 2 minutes or so. Then from there, we'll move directly to the Q&A period. All right, well, thanks, everybody. Give these just a couple of minutes, and then we'll move forward to the question and answers. Okay, everybody, we will give the polling questions just another 30 seconds or so, and we'll move directly to the Q&A period. Okay, everybody, let's move to the Q&A period. And have questions, I'd like for you to type those in here. For those of you who asked about whether or not the presentations would be available for download, yes, what you'll see below in the lower right-hand corner of your screen, you will see the first 3 demos with the e-learning tutorials and the 2 script demos for ASTER Level 1T. This webinar is being recorded, so the recording links will be sent out to all participants within a couple of days and registrants within a couple of days of completion. And then you've got the slide deck down below as well. If you click on any of the files, you'll be prompted to download. Just check and see if we have any questions here. Does anybody have any questions? Okay, let's see here. Okay, do these functions work on a Mac, either Cole or Aaron?
You know, I think we've had a couple issues with Mac users. We don't actually have, between the 2 of us, don't have a Mac to test on. And so there seems to be more issues when you are looking at the metadata. The actual importing of the data values doesn't seem to be affected, but depending on, I guess, your operating system or even your GDAL version, you could get a different list. You could get a compacted list of metadata depending on your version of GDAL. And so how you actually string subset that stuff kind of varies between the 2 operating systems. And so that's kind of been our experience at this point.
Yeah, it should work on a Mac. The biggest thing is if you are having issues on a Mac, I would check with your GDAL version before you come to us with questions. Because that's the biggest source of differences in how it actually reads the file metadata. It's based on the actual version of GDAL that's installed.
Okay, thanks. Our next question is, does the quality service contain the quality layers in a config file? Does it query the metadata to determine if it is a quality variable?
No, you have to explicitly specify what quality layer you're talking about. The service draws from some more or less lookup tables that we've developed beforehand for each quality layer, and so it will query basically those tables to give you the correct output for a quality value.
Okay, thank you, Aaron. Are there additional questions? Anybody? Okay, while we're waiting to see if there are additional questions, what we'll do here when the Q&A period is over, I will leave the virtual meeting space open an additional 10 minutes or so to, depending on when we finish, for people to have an opportunity to download the files, but we will log off from the audio component of the webinar. However, if you think of any questions or have any additional comments that you'd like to convey to us and the speakers, please enter those into the Q&A pod. Here's an additional question here. One second. Do you have any scripts for geolocation?
Level 2
data. Might have to be a bit more specific on that one.
For level 2 data.
Oh, for level 2? No scripts right now, no.
Okay, thank you. And our next question is, how do these tools compare with NV?
We've never done direct comparison with NV. I mean, what Python and R are offering are kind of less clicks, right? It's more streamlined. The upfront effort to get something developed and operational for yourself is probably more than what you would experience with NV, but after you get that protocol, I guess, set up, it's pretty easy to slightly modify and execute on a different set of data. And so as far as performance, we haven't done any direct testing.
Okay, thank you. And then the further clarification on the earlier question regarding the scripts for geolocation, the reference was level 2 swath data.
Yeah, we do not have any scripts for geolocation of level 2 swath data at this time.
Okay, thank you. And the next question is, have you tried these scripts on the new Landsat Collection 1 images?
No, we have not tried these scripts on Landsat.
Okay, and we have an additional question here. Can these scripts be adapted to other satellite data?
For sure. The I guess, lessons within can definitely be applied and modified. You probably won't be able to, I mean, do an exact match, but if you know, especially for like the HDF file, if you know how to kind of parse the hierarchy of that HDF file, it's pretty easy to expand, I mean, that to other HDF files. And generally, I mean, HDF EOS 5 is a NASA standard, and so they technically should have a very, very close structure. So you should be able to navigate one data set that's stored at one location in the same manner that you navigate a data set from here.
Yeah, I'll just add too, and absolutely, I mean, the workflow itself should be very, very similar. So say if you took the VIIRS script and you were interested in working with MODIS data, you should be able to look at what's going on in the VIIRS script and adapt that to your specific needs for whichever MODIS product you're interested in looking at, particularly in terms of the workflow of setting up your environment.
Okay, thank you. Are there any additional questions? Right now what I'm going to do, let me scroll down again to see. Yes, there is. Okay, so the next question is, R has memory issues with large files. What's the best option to handle them?
To be honest, my best answer to that would be if you're having an issue with working with very large files in R, I would consider moving into Python. Not only can you handle larger files in Python, but it will be a lot faster than working in R. If that is not an option, I would recommend splitting your files into smaller tiles. I've actually had to do this before where I'll split a single raster array into multiple raster arrays, bring one in at a time, actually run all my calculations on it, and then remove it from memory, and then upload the second tile and keep going that way. So those are two potential options.
Okay, great. And what I've done right here is type into the Q&A pod 2 resources for end-user data inquiries or script questions or any kind of question you have with respect to their data holdings, and that is the User Services Office email, which is lpdac@usgs.gov, or the submitting a ticket through our more centralized Earthdata support system, which is support@earthdata.nasa.gov. Are there additional questions? Space open for all of you. All right, so thanks to our speakers, Cole and Aaron, and thanks to all of you for listening in on today's webinar.
Thank you, everyone.
All right, thanks, everybody. All right, bye-bye now.
Bye.